I hope that this lecture doesn't help you to sleep after lunch, but I will do my best. So this is just what we did yesterday, a general introduction about a Hamiltonian damped system and the variables, then some words about the context, and then the variational statement of the problem. So I will just to recall briefly some points. So this is our system. So we have a set of hidden variables and the master that is actually the focus of our investigation, the red ball. These are the complete set of equations, and we had split the Lagrangian function into three terms. We indicate with x star, x flex star the solution of this set of equations. So our hope is just to erase the hidden part of the system and substituting the part that depends on the hidden variables by a suitable function in order to write down a single equation just for the degree of freedom that we want to monitor. That's it. So we want to replace this complex expression just in terms of something that can be expressed only in terms of the master variable, so that in terms of the coordinates of the variable that we are observing. And of course we ask that x star would be the solution of this equation. So actually, as I told you yesterday, our first point is to provide a general model for V. So we want to understand what is the contribution that comes into the master equation coming from the interaction with the hidden variables, so the environment in which our particle is placed. And we will develop now a theory that is limited to linear systems. So just a couple of definitions because they were kindly asked by my friend Francesco. So the first definition, what is the system definition for energy invariant? That is a collective property of the motion. So we have this Lagrangian function, then we have the Hamiltonian, and so actually we have that the energy in the system during the motion is preserved. That means the time derivative of h is equal to 0. Definition 2, damping, that is indeed the local property, so it is not related to the collective motion. We say that damping is observed if one of the coordinates has an energy that is decreasing, and it happens within a particular time interval. So we require that for a time interval, T(A), T(B), we see that the local energy decreases. So within this interval, we say that we are observing damping. So we want to just focus on linear systems. So we take quite a usual expression for the Lagrangian. So I see that one sign is wrong, but so we have just quadratic form in terms of velocity and displacement. That's it. And then we have two matrices that we can call M and K in order to produce this quadratic form. About the nature, the physical nature of the matrix M and K, there is any kind of limitation. So we can think about mechanical problem as well as to electromagnetic problem or couplet problems. So
K is positive.
See, that's positive defined. Yeah, it's minus. So yeah, it is wrong, the sign. Yeah, I told before that the sign is wrong. So we have no special hypothesis on the matrix key, except the one that has been recalled here. And we want just to split and partition the matrices in order to emphasize the part that is related to the hidden variables and the part that is related to the monitored variable. So this is a partition that we will use in the following. So actually the complete matrix K0 has the first row, that is K00 up to K0n, and the first column starting from K00 to Kn0 that are of course the transposed of a certain vector and the vector itself. And the submatrix that is key flex that just contains the coupling terms, elastic coupling terms, if it is a mechanical system, that are related to the that are just related to our monitored system. So these are simply the equation that we can write down. So our problem is just to partitioning this equation, just using this expression, in which it is a trivial separation of terms depending on the particle that is under observation and the variables that just related to the hidden variables. And then you can see that you have a first term here that is just dependent on the coordinates of the observed particle. Then you have mixed terms, and then you have something that is just related to the hidden part of the system. And then we can add some parts that are related to external forces. Say that in the next steps, the external forces, especially the ones applied to the hidden part of the system, are conceptually not elegant, in my opinion, because this point of view is that you are describing a part of the system that you are observing and the rest of the world. So force means that there is another system within which we are interacting. So if the hidden variables represent the remaining part of the world, of course there are no force on it. So I think that the best way to represent our problem is just to say that the F flex force is equal to 0. So it means that we are considering the universe that is interacting with our particle. But it is not, of course, a mathematical problem, but just a physical problem or philosophical problem. So we can split the equation in this way. So this is the first, is just the first equation related to the x variable, that is our master structure. And then the following n equations are the equations for the hidden systems. And then we can represent in a very short and synthetic form the equation this way. So actually the equations are very simple. Nevertheless, we will discover something that is quite intriguing and interesting. So actually what is our goal now? It's very understandable. So I want in some sense to solve the second set of equations in terms of x, just considering x has a known term. Then I want to solve these equations in terms of x flex. So suppose that x flex is considered in this equation the unknown, but you consider x as a known term. I put it on the right hand side, then I solve for x flex, and I go to substitute into the first, in order that these terms must be expressed in terms just of x 0, x, no 0, x. Okay? So this is just the strategy to obtain a single equation just in terms of x. So this is just a comparison between the linear case and the general case. So we see that the equations are very easily determined. So our goal, as I mentioned it before, is just to erase the second set of equations, and then this is the comparison between the two terms. So actually we answered our first question. So what is, for a linear system, the explicit expression of the part that depends on the hidden variable that interact with our particle? Just a linear combination using this key flux vector. It's just a linear combination of the response of the hidden part of the system. So our next point is just to transform this key flex, x flex, in terms just of x, its derivative, or some integral related to this variable. So I can show you if you want quite in details, but I think that maybe not now. So explicitly, how we can do this kind of transformation. So the first step is just to consider the Laplace transform of the whole set of equations, because it is very easy to produce these results. So the strategy is very easy if you apply Laplace transform. Then you can solve for the hidden variables in terms of x in the second set, and then you can substitute solution for hidden variables into the master equation. And then you can go back to the time domain just performing an inverse Laplace transform. It's quite an obvious operation. So I would like not to go into say, mathematical details that are just algebraic details. So if it is sufficiently clear that this is the procedure, I think that we don't need really to add very much to this. So we can look at the final expression that we have for our system. So as it is obvious, we have the inertia term, then we have a direct elastic term, then we have something that is a convolution integral between something that is related to spectral properties of the hidden variables, that is contained, this information is contained into the G matrix. And you have a convolution between these two in order to produce the effect that the hidden variable have on the test particle, the monitored particle of our system. So it is clear that after we produce this Laplace transform, then we have just to solve algebraically the problem. And then, of course, when you go back to the time domain, you just have a convolution integral between the response.
Zero for negative argument.
Yes, it is. So on the right-hand side, so I would like just to, maybe that tomorrow we will go into some other details. But since this is a last day that Victor is here, I would like to just avoid these details just for have time to show you something that is more interesting than not these mathematical details. What we have on the right-hand side, we have the force that F0 that is directly applied to the observed particles. Then we have another convolution that is the convolution of the G function that represent actually nothing else that the spectral properties of the hidden part of the system. And then we have Flex that is the force applied to the hidden part of our system. So as we mentioned before, we can erase this term. It is not really very much interesting in some sense. This is an additional term that we can introduce during the Laplace transformer invention if you want to take into account initial conditions. So say that the main point is on the right hand side, and for this reason this is the right hand side, we included all the terms that are not directly depending on the variable x. So it is a sort of say a sort of noise. So it is something that is a function of time, and actually depending on initial conditions that you impose on your system and depending eventually on the form of the force Flex has some particular spectral properties. So actually at the end of the day what we have is the trivial terms, these three, force, elastic, direct, and inertia. Then we have an interaction term. This is very interesting. And then we have a sort of noise that is exciting our particle. Well, it is really a quite good picture of the problem. And of course, actually we can now study what are special properties for G in order to have, for this kind of contribution, something that would represent dissipation. Okay? I would like just to note that there is a quite very special case in which we can have a flavor of what is coming out from this equation. So just the case in which you have that the G matrix is something that is a close relative to a delta function. It's produce something that could be a sort of elastic force. Or if you represent this just without considering G, but considering G prime, and then we convolute G prime with something that is x dot. It is easy to transform this into this form. If G prime is something that is a delta function, you obtain here exactly a dissipation term. Of course, it is just a mathematical representation of what we have in mind, because the conditions under which G has these properties are not trivial at all. But it suggests that depending on the structure that G has, we can introduce in the motion of our system something that is a true dissipation, or say apparent dissipation, because it is a damping for our system, that correspond actually, just as we know, to a transfer of energy from the particle that we are observing to the remaining part of the system. So I think that it is very tricky, this equation. And I would like just to illustrate to you very simple examples for this. So if you suppose, for example, just think about a very simple mechanical system. Suppose that this is our oscillator, very easy. And then suppose that this mass is a piston, and the piston is in contact with a very long pipe in which you have gas, for example, air. Then I give initial condition to the piston oscillates, waves are propagated along the waveguide. Of course, I'm transferring energy from this piston to the air that is inside. It is obvious that this kind of process does not involve in this model any kind of dissipation, actually. So the energy is just transferred from this element to the air that is inside the pipe. So there is not any actual mechanism for real dissipation in the system. But actually the energy is going from this system to this system. It is very nice to see that if you want just to solve this problem, you can just observe the piston with a spring, and then of course it is expressed by an equation like m0 x double dot plus k0 x. Of course there is something that represents for this system a dissipation. But the parameter that controls the dissipation of this system actually has nothing to do with a principle of energy dissipation. So if you make the calculation of this very simple system, you will find that it behaves exactly in this way, in which you have an equivalent damping that is just expressed in terms of the stiffness of the material that is contained in the waveguide, the section, and the speed of the waves along the pipe. So three parameters that have nothing to do with real dissipation mechanisms.
X dot or
X dot.
X? There are no double dot.
There is no double dot? Yeah, there is, but they are... Okay.
On the last,
It is dot.
it's a spot, which makes believe there is
Okay.
a double dot.
No, just one dot. Okay? So if I'm not wrong, I made this calculation. It is the equivalent is something like the Young modulus, the cross section of this system. It is divided times the longitudinal wave speed. This is something. This observation is something that can help to understand what is the physical meaning of this interaction term. Of course. But there is, I would like just to try to modify the view that we have of dissipation. Because this example actually is instructive in order to understand a quite particular point. In many cases in engineering, we want to control damping of a structure. But as you know, it is not easy to control the damping in a structure, because generally damping is something that we can add, but we have a certain difficulty to control. For example, if I want to have an higher damping at the center frequency or a small damping at other frequency, we know, for example, if you examine just the single degrees of freedom resonator, that when you introduce damping, the damping has a good effect around the resonance. But in high frequency, so to have an high damping can be even worse. So we can, in some cases, to have a better control for damping. This example shows very clearly that we can act, or we can modify, or we can control the damping of a system acting on stiffness parameter of the other part of a system, of parts that are far away from the particle or from the system that we are studying.
Could you explain how, what, say, in your example, what would be G? How do you get from this integral?
Oh, well, it is quite, so it takes some time, but the concept is very easy. You have just to compute what is the impedance of the system that is connected to the 1 degree of freedom system. Then you compute the impedance, and then you compute the inverse Laplace transform of the impedance. It is the input.
Real gas, so I mean continuum, continuum model of a gas.
Yeah.
Right. Then there might be some, and the other end of the pipe is closed.
Okay. This is the very good question. That is just the red line for the following point. So I was waiting this question. Sorry. The main point is that if the pipe is infinitely long, the effect that you have is just a pure dissipation effect. But you need to have an infinite long pipe. What happens if you have a finite length pipe? If you have a finite length pipe, what we can expect is before the wave that is flowing through the pipe doesn't know that there is an end, the equation is like this. Nothing is changed. But when the gas recognizes there is a reflection at the end, and then you have a reflected wave that is coming back, you have that some energy that you transmitted to the remaining part of the system comes back to the resonator. So what we expect is that in general the characteristic of this term is much more complicated for finite systems, and in fact it is indeed the case. So what we expect is that at least for some time windows we can expect that the energy is irreversibly transferred to the environment. If the environment is finite, we expect that after a while we have some echoes from the system. And then in this case, of course, this is not representative of a real dissipation. So this is an exact result, of course. Yeah. This thing takes into account everything. But our goal is to obtain from this expression something that is as close as possible to the case of infinite waveguide. And we will see what we intend the closest possible in order to mimicking with a finite system the effect of an infinite system. And this is just so the intuition is that if you have a special population, so we know that G depends mainly on the spectral characteristic of the system. So in particular it depends on the natural frequencies of the frequency that is the hidden part. So if we approach the problem in a statistical way, just like you had shown this morning. So we want to approach the problem in a statistical way, and so our question is, suppose that the remaining part of the system, especially because generally you have to do with a very large system with many degrees of freedom, with many frequencies, on which, because of the hypothesis, I don't want to go into mathematical details, so it means it is reasonable that I assume that I have some uncertainties about that. Then I can approach the problem in terms of probability. And then I say, the natural frequencies of the system are unknown. I would like to assume that the problem is a random problem in terms of parameters of the system. I'm looking for the probability density distribution of the environment that does its best in order to imitate this behavior. And then we can find an analytical solution for the problem. This is just the last step. This is just to give the flavor of what we want to do.
Is it possible just to write explicit formula in terms of eigenfrequencies, right?
Yeah.
I guess it is quite simple.
It is a green function.
Green function.
So it has actually, I will show you in the next slides. So I would like to propose just two simple examples about the way that we can understand the nature of this kind of kernel, G kernel. So we have G kernel. The representation could be both in time and frequency domain. So we have in the previous equation we have a convolution. Then we can represent G as a function of time, or we can represent G in the function of omega, or in the function of the S that is Laplace variable. It's the same. So I would like just to propose a first approach, that just to understand what are the characteristics that come out from this analysis. The first point is, suppose that the motion of the system can be reasonably expressed using for GS just a linear expansion. So we have that G of S is a complicated function of the frequency. Okay? Suppose now that we can use for it a Taylor series expansion and assume that we use a first order Taylor series expansion. So we can put the first term, the second term, the linear one, and then we have a remainder term that is expressed by the Cauchy integral. And suppose that we use a brutal expansion, meaning that we kill the remainder term, just to have an idea of what happens. But we will go back on this point. Then we say that I can assume that there is an initial point for the Taylor expansion. Suppose it is in the complex plane, sigma 0 and omega 0. And then suppose that the S variable is just along the imaginary axis. So I can, in general, have the complex plane. I can take just the point S0. And suppose that I can use a circle around S0, and then I can use this kind of approximation. But I'm just reading what happens along this segment. As a special case, you can assume sigma 0 is equal to 0, but it is not important really at this point. So it is just a trivial computation. So I put this expansion into the GS, and then I take this expression. And this is something that is very intriguing. What we have here, of course, it is just a Taylor expansion, so it contains constant and a first order terms in terms of omega. So a linear term in terms of omega and a constant term. We have to introduce another distinction because this linear term and this constant term can be real and complex. So we have 4 terms here: real and constant, real and linear, imaginary constant, and imaginary linear. So they correspond to 4 different effects in our system. And I would like just to briefly examine this effect with you. Before to do this, we have just to recall a couple of definitions. Not the first. The first is just the trivial definition of inverse Fourier transform. But we need to introduce a couple of concepts. One is related to the Hilbert transform, and the second one is related to the so-called analytic signal, or the one-sided Fourier transform. I don't know if you are familiar with this concept, but they are very easily explained, at least if we go now too in-depth. Okay, this is just the inverse Fourier transform. So suppose now that you have a function x. Then I can take, so this is time domain. Here you have the frequency domain. Then I can take the image of x that is capital X. Then in this domain, I just modify the components, the frequency component of the signal, just introducing this nice function. It is minus the j sine of omega. So what I'm really doing is that you consider the Fourier transform of your signal, or something like that. Then I multiply the signal by minus j sine of omega, meaning that in this part I multiply by minus j, and this part is multiplied by plus j. Okay? It's easy. So I can take, for example, I have MATLAB, I perform just the Fourier transform, then I take the file with the Fourier transform, I multiply the positive frequency part by minus j, and the negative part is multiplied by plus j. Then I take this signal and I convert it back to time domain. This is the Hilbert transform of the signal. What is the meaning? It is just, in signal analysis, it can be called a phase shifter. So you are just considering the component of the signal, you are multiplying it by j, meaning that you are just shifting each component by pi over 2 on one side and minus pi over 2 in the negative part of the frequency. Okay? It's quite easy. Then you can take, but it is nice because it permits, in our case, to express in a very clear form what is the action of our convolution integral. So what is the fact of interaction between the particle that we are observing and the remaining part of the system. Then there is this second concept that is just the one-sided Fourier transform. One-sided Fourier transform means that you take the Fourier transform of your signal, then you erase half of the signal, so you erase this part, and then you transform back to the time domain. And then you obtain the so-called analytic signal. It's very easy, by simple combination of the signal, to see that the one-sided Fourier transform is just 1/2 summation of a complex signal that has the real part that is just x, and the imaginary part that is the Hilbert transform of our signal. This is useful for what we are doing now. So these are the 4 components that we introduced. We have just to understand what is the physical meaning of the 4 terms. So it's clear that since from our expansion we have 4 terms, I would like to say that at least the 2 are trivial. The other 2 a little bit more complicated. So the linear term in omega that is real, well, it is somehow difficult. The constant in omega that is indeed imaginary is a little bit complicated. The 2 terms that we can understand very easily is the linear part that is imaginary, and the other one is the constant of omega that is real. So these 4 contributions. What does it mean that we have in the frequency domain something that is linear in omega and is imaginary? It means that you are just dealing with a term like that, j omega. What does it mean in its counterpart in the time domain? It's just something that depends on x dot. So it's easy. It is a viscous damping term. So it is viscous damping. So it's easy to understand. Constant and real. Of course, it is an elastic term. So it means that you have something that is just proportional to some constant. So you have that there is something that is an equivalent constant, and just multiply it by x. And this is just an elastic term. What is constant and imaginary? Many times in mechanical engineering, there is introduced the concept in a very, it's an awful way to introduce a damping that is called hysteretic damping. So if you have an harmonic oscillator, it's quite natural to introduce something that is dissipating energy in this form. Then you have an elastic term like that, and then you have a force. But if you introduce something that is, for example, the Fourier transform of it, you have something that is like that. Then you have j omega x plus kx. It's f. So actually what you see in terms of frequency, if this is the dissipative force, you have that dissipation force is increasing linearly with omega. We know that experimentally sometimes dissipation does not act this way. So somebody introduced something that is some effective dissipation that is actually not controlled by frequency. So one say, well, we have something that is just like this with h is a constant. The problem comes when you want to have a time domain representation of this equation. Generally, they say it is valid for monoharmonic signal. That is meaningless, because in reality you have not a monoharmonic signal, so you do not know what is the corresponding counterpart. But actually it's very easy to see that the counterpart for this effect in the time domain is just represented by Hilbert transform of our signal. So the final picture is very nice. So if we take a Taylor series expansion, what we get is the usual trivial terms, inertia, and direct elastic force applied to the spring. Then you have four additional terms, 1, 2, 3, and 4. This is the one that is just related to this, linear and imaginary, viscous damping. Then you have this that represents in the frequency domain just something that is j times directly x. And this is hysteretic damping. And this is something that we call gyroscopic effect. We say just gyroscopic effect because it depends on something that is related to the derivative. When you have a term that depends on the derivative, but it is not dissipative, the only effect that I know that can depend on velocity and is conservative is just the gyro effect. So we say gyro, equivalent gyro effect. So this is the picture for our system. The very nice thing is that it shows that you can obtain something that is a real dissipation. So you obtain something that is a dissipation of energy if C equivalent and it equivalent are positive, because they depend on the Taylor expansion, but they can be selected in this way. These are two dissipative terms, and then you have this elastic term and this gyro term that are indeed reactive term. So, sorry?
X flex, as you say. This is unknown.
Oh no, sorry. This is a Hilbert transform. It is not the x flux. No, sorry. It is a wrong notation. But say the x flux means that it is just a Hilbert transform of x. So it is just an differential integral. Oh, it is just an integral transform of x.
Is it possible to write?
Oh well, you can just define it looking at the image. in the frequency domain. So this is the recipe. You take the Fourier transform of x, then you multiply the spectrum by the function j, and then you take the inverse transform. Otherwise, you can use another definition that is based on a principal value. So you can show that this definition is just equivalent to consider this integral transform that is 1 over pi. It's the integral minus infinite plus infinite, that is x tau, it is tau minus t, the tau, and this is a principal value, of course. Okay, and that's it. It is more understandable, that definition, but if you at the end want to write in a more concise form, then you can.
Frequency dependent?
No, this one?
Yeah.
No, it is not.
It is not.
It is not. This is just the characteristic of this term, is that it is not frequency dependent. So if you look at the way the dissipation force goes with, so you have a dissipation force with omega, so you have, this is viscous, this is hysteretic. Okay? Then, what we get is quite intriguing. If you just, for fun, if you just use a zeroth order expansion, you simplify the expression this way.
Is this, could it be called dissipation in the sense that energy of your oscillator decays?
Decay.
This,
Exactly. It is exactly. So this is the main characteristic.
So you can prove that for such an oscillator, total energy of
decreases. But we obtained this result under a quite strong and brutal hypothesis. The brutal hypothesis is that we assumed this Taylor series expansion, and we neglect definitely the remainder term. So one can ask at this point several embarrassing questions. Say that, put a list of key questions about the remainder. The question Q1, what is the effect of a remainder term on the motion of x? So we neglected it, but may well be that it has an effect. So in some sense we can suppose, starting from your previous remark, suppose that we are dealing with a finite system. Now, just considering the Taylor expansion, we have something that corresponds to an irreversible process, meaning that energy goes and doesn't come back. Does it mean that actually we are considering an infinite system? So maybe that the neglection of the remainder correspond to have an infinite system instead of having a finite one. So the question Q2 is, can the time domain counterpart of the remainder term disclose some elements answering the previous question? And again, in which manner the form of the remainder term depends on the physical system properties? Another interesting question that comes from the previous remark, the presence of these pseudo-dissipative terms that is based on this energy release to the hidden variables, is a permanent property of the system, or the existence of a not negligible remainder confine this effect at some time window. So meaning that this is not a permanent property, but it's just a transient property. So if we observe the system for a limited time, we observe this. But may well be that after a long time we have that long or short. It's not clear.
Maybe this question is formulated in terms of how much time you need to wait.
Yes.
If it is Hamiltonian,
yeah.
it will go back.
Oh, yes, it will go back. The problem is that the characteristic time length that you have to wait in order to see. But in this case, the time, depending on the system, can be short. So it's. Then we have two technical questions. So we can imagine if there exists physical system that can purposely selected or designed for which the effect of the remainder term can be controlled, for example, making it as small as possible. So I want to design, in this case, a special system that is capable of absorbing the energy, trapping it, and it is able to keep this energy definitely, or practically definitely, into the set of oscillator without leaving it back. The last question is, there is any chance to use this concept in order to design special engineering device? And the question has a positive answer. So we want to, in order to give an answer to the questions that we put about the remainder term, it is very difficult to be formulated just starting from a Taylor series expansion. So there is a more smart form to approach the problem. But it is formally different and it permits to understand better the nature of the system and especially permit to understand what is the effect of the remainder term. So the question is very easy. G d omega is just the transfer function of the system that we are coupling to our oscillator. So we can express simply this function in this way, and this answers the question you put before. So what is the form, the characteristic form? You have that omega is just the Fourier transform, is the Fourier variable, and omega n is the natural frequency of the system. Then you can use this of hidden variables. So you can use this expansion, and after some calculations that are not really very exciting, so I can show you just the final result, you can approach again to a convolution integral. But this time, so I used here this kind of integration. Then you have a kernel that is just represented in this way, that is more clearly related, as you asked, to the spectral properties of the hidden system. So actually we have just a combination of harmonic functions in terms of natural frequencies. And h is just the Heaviside function. In order to otherwise I have to write this integral. If I chop this term, I have to limit this extreme to t. So I want to, it's more useful to include h and having this. So this is an exact result. So there is not approximation, please.
The natural frequency of the hidden system.
It means that, it means that this is my oscillator. It is connected to a very complicated environment. I disconnect this one and I study what is the response.
Not really the frequencies of the hidden system.
I can call it, so you can suppose that you can perform a test. So I attach here an oscillator to this, to the word, to the remaining part of the word. Then I disconnect the oscillator and I want just to investigate what are the natural frequency of the rest of the word except the oscillator that I introduced there. And this is the meaning of the natural frequencies that we have here. Well, this is in my opinion, this is a quite more comfortable picture of the problem. But there is something that is very uncomfortable still. It is the form of the kernel ST. This is a very difficult guy to deal with, because you have summation of harmonic functions with different frequencies. It is something that it is very difficult to treat mathematically.
Could you say anything about the signs of these constants better? Or do they have certain sign?
No, it is difficult because, so you are referring to the nature of the beta. Well, it is difficult. That depends on the mode shape. Mode shapes meaning the eigenvectors.
So they can be of both sides?
Yeah, they can be. It depends on the system that you are considering. In some cases, they are all positive, but it is not the general case. So in order to go a step forward, we want just to associate to this summation a corresponding integral. Suppose that you have many natural frequencies, and these natural frequencies live in a quite narrow band. It is reasonable to say that this discrete summation can be well interpreted by an integral, but this will be a very delicate point. But suppose that we can do that. So actually what we can do without any kind of error is just to say that this integral that we want to replace in our correlation function can be just expressed as a summation of the original discrete summation plus a remainder term. But in this case, the remainder term is much more tractable than in the last case, and can be used in order to understand much more intriguing concepts. So I just substitute into the previous equation this new expression for the integral, but I have, of course, a second term that is a remainder term. And about that, I don't want to tell something now because I have some explicit expression for RT. But since tomorrow you are not here, I prefer to go to the optimization part. So suppose that we neglect the remainder term. This is the final picture of the problem. But we have just to remind that we are putting, in this case, we are forcing the remainder term to 0. This is something that we don't want to do without a deep discussion. And then we can look later at what are the consequences of putting and forcing this remainder term to 0. For now we say, suppose that the remainder term can be neglected. I would like to know what comes out from this picture. So the very important point is just this kernel that is just H, that is Heaviside.
This is integration over C from 0 to 1.
Oh, because just the psi is a dummy variable.
So you just scaled somehow.
Yeah, it is. We scaled something that is the psi is times n is the n.
And n is the number of total number of
oscillator, yeah.
Of number of
the exophenol of the remaining part. So we want to understand this, and then we can use exactly the same technique that we illustrated before. So we can transform into the frequency domain. Again, I don't want to show you mathematical details, so please trust me for this result. And this is very interesting to me. So we are just considering that this is minus. It is not here, I don't know why. It is minus. So we are just taking the Fourier transform of this term, because of course if you take the complete Fourier transform of this equation, you obtain minus omega square, then you have m0 x0 plus k00 x0 plus 2 over n, then you have the transform of the convolution, that is x0, times this 1 over n, the Fourier transform of h times I equal to f0. That is what we are doing. So the nature of this Fourier transform gives and provides direct information about the nature, the physical nature of this term. What we have here, we have an imaginary part and the real part. So the imaginary part is responsible for the dissipation in the system, dissipation upper and dissipation damping in the system. The nice thing to see is that it depends on the natural distribution of eigenfrequencies. So this is nothing else that the natural distribution of eigenfrequencies in the sense that is very similar, and we will use this fact, to the probability density function of them. Actually, we up to this moment we didn't introduce any kind of statistics here. But what is the n over the omega here is something that is very easy. So you have omega here. You have something that could be a distribution, meaning that if you take a bandwidth, delta omega, so this area provides just the number of natural frequencies that fall into this interval. So it is, say, the sister of the probability density function. So we are just not introducing here any statistical concept, but it's clear that it is here. So this is a very intriguing point, because it means that if we are able to control this quantity, we are able to control the performance of the device. At the same time, we have another reactive term that it is indeed independent of dissipation. Several considerations about some physical system can lead to the conclusion that in general, even if the Fourier transform of this term is small, since this term is responsible for damping, and this equation does not contain any kind of damping, this is definitely important as a damping term. Indeed, this term is a reactive term that, as a first approximation, has the same effect as this, but generally his importance with respect to the amplitude of K00 is of minor importance. So generally, we neglect the reactive part and just take into account the dissipation part. That is the most important contribution that comes from this integral. If we introduce also the previous notion of motion about a given frequency, so we can introduce, for example, an approximation for this, we can take an equation that is like this. So actually we have a sort of effective damping into the system. Well, this is actually the first part of our presentation. Starting from this point, our question is can be formulated in this way. We introduced an hypothesis that is quite heavy. That is, a remainder term is negligible. It is possible to assume this kind of condition. If this is possible, it means that you obtain an equivalent damping into the system. So what we have to discuss is this remainder term. So we can discuss this tomorrow. So just looking at what are the properties of this, and from the analysis of this term we can find readily the time window over which this equation can emulate a dissipative system.
What is
Omega 0?
omega 0?
Is just a reference frequency. So we use the hypothesis that in that case that you have a bandwidth in which you have the natural frequencies that is narrow. So omega 0 is
the natural frequencies of hidden variables.
Yes, of course. And this is reference frequency for this bandwidth.
Now, how would it be if you have system with very many degrees of freedom?
Well, because suppose I'm thinking to an inverse problem. So I'm mainly attracted to the design part of the problem. Suppose that I built up purposely the system having the frequencies that are close in a narrow band.
So you have a system, all eigenfrequencies of which fall in a very narrow range.
Narrow range.
Right? So
because I built up the system this way.
So for such type of system, you expect to to get this boxed equation.
Yeah. Okay, this is an approximation, but
Yeah.
it works. But the problem now is, what about the remainder term? So the next part of the presentation, so I was chopping many parts of this in order to just to give you the second part. So the idea is, I cannot select. So you have this. This is the summation that depends on the natural frequencies, omega n, the set of natural frequencies. Say that is a vector, and then you have the integral that depends on time and depends on the, say, on the function omega psi. Then I have not a way to reduce to zero RT, but I can ask that IT and ST are the closest possible by suitable selection of this distribution. These are, we can have a double way of reasoning. So I can reason in terms of deterministic problem, or it is, say, more suggestive in some sense to talk about a probabilistic problem. If I talk about a deterministic problem, omega xi, meaning just that you have to design purposely the system in order to have a certain distribution of frequency. But of course, the result can be interpreted in a way that, say that I put frequency at random just using some constraints. So you have to have a distribution that is of some kind. So the problem can be looked at in this very simple. It is not simple, but it is quite a reasonable idea. S appears as something that is a summation of some quantity. I put here just 1 over n. And then integral, the integral I that we are considering is just, if you have here something that is summation of some quantities, it is just something like that. So the idea is, suppose that we can interpret this one has the arithmetic mean of something that are random variables like sigma I. These are just sample of a random variable, because of course if I have random frequencies, I have something in the summation that is random. Indeed, the integral, this is the arithmetic mean, meaning is just an estimator of the mean of this function, while this is the exact value for the mean value. Now I can put the question in a very sharp form in terms of stochastic problem. So I can ask exactly the same question, or very close question, to the one that you posed this morning. I can ask to minimize the distance between this integral and this summation. So I can ask that the average of S minus this integral squared is minimum. But this is definitely a variational problem, because this, that is the variance of the problem, directly depends on the selection of the distribution of probability you have there. There is a beautiful theorem that was discovered in 1943 that is called the Cramer-Rao inequality, that establish a very nice point. This is called the estimator for this exact mean. So this is the exact mean, and this is an estimator of the exact mean. So this is the estimator that we use generally computing arithmetic average. Well, if you want to ask if there is a minimum for this, the question has a sharp answer. We have definitely distributions that are more lucky than others. So there are the so-called distribution for sufficient statistics that have the beautiful property that they can match the possible minimum for this variance. So this variance cannot be 0. The variance has a minimum incompressible value. Now, you can set that there is a minimum, sharp minimum at this point. So what is the best I can do is just to select p sigma, so the distribution of probability, in order to keep the minimum that is called the minimum variance bound. So if I can keep this minimum, so I'm trying to find the distribution that produces just the minimum for this function. For the translation in our problem, it means that we are just selecting the distribution that provides, as close as possible, an irreversible effect. So I have some, how is possible to, how we can ask from, okay. So just, I can understand that, okay, so this is the variational theorem for the minimum remainder term and its probabilistic interpretation. Actually, I compacted the two, so it is just directly the interpretation. Okay, this is just, okay, suppose that our uncertain system has natural frequencies that are omega 1, omega 2, omega n, that are random variables. So we have a joint probability distribution that is P1 to n. And so the first hypothesis is that the natural frequency are statistically independent. It's something that we can assume. So we have just the product of the single individual probability distribution for each frequency. So second hypothesis, the individual PDF are all equal, meaning that we just introduced one variable in our problem. So it can be generalized, but it is a little bit complicated. So the question is, there exists a relationship between the PDF that can lead to an irreversible energy confinement into the hidden variables. And the second question, there are PDF forms that are sufficient to produce an irreversible energy confinement. So we can discuss the problem in general, considering that it is exactly the same thing that we were doing before, that for a general system we can just write down the impulse response, if you want, like this function, just a combination of harmonic functions. So if you have a system, then you put an impulse at some point. So the motion is described by a function like that. It's just a combination of harmonic function in times. Each harmonic takes the information about the natural frequency. So this is the impulse response of a single sample. Suppose that this is a, I don't remember, this is a beam, I guess. And this is an almost periodic function, so it has a very complicated trend in time. So we don't want to go to investigate it. But suppose that now you have that the omega I are random functions. So I can reasonably associate to this the ensemble average for the impulse response function. So I can consider a sort of population of systems. They are differently equipped with natural frequencies. So each sample has different natural frequency from each other. Then I can compute the average of the impulse response, just giving this integral of the joint probability function times the characteristic ht. So we can use both the hypotheses that we introduced. So the natural frequency are statistically independent and the individual PDF are all equal. So this is actually what we can do. This is the expected value of the of the impulse response of the population of system that we can consider. And PD omega in our problem is the unknown. So I want to select properly P of omega. Well, we have to now understand a very nice property that has the average of the impulse response of our system. If you just take this expression and then you use an integration by part, is very commonly called a symptotic expansion of an integral, or Watson lemma. Watson lemma. With a Watson lemma, we have that it's very easy to show that the asymptotic property holds, meaning that if you take for your population of system the ensemble average of the impulse response for t large, you approach 0. So the impulse response vanishes for large times, at large times. This is a very interesting property because it means that the system that we are investigating, even if it is finite, suppose that you have a system like this, but it's finite. If you take a population of random system like this, in which you have a distribution of characteristic properties of the natural frequencies of this pipe, and then you take the impulse response of this pipe, and you take the average, well, the average has this property, so it tends to vanish. This is not a property that the average shares with the single sample. The single sample has oscillations and has energy that comes back from the end. But this property is not shared by the ensemble average. The ensemble average has this very nice asymptotic property. And in fact, the impulse response of the sample and ensemble average do not share in general this asymptotic property. And I would like to show you a very clear example of this. This is very instructive because it's very simple. Suppose that we have a family of 2 degrees of freedom. So I consider an ensemble of 10,000 systems modifying randomly the springs constant. Okay? Then I compare the response of a single sample. It is obvious to see that the single sample has a periodic response. It's just a 2 degrees of freedom system. And this is the ensemble average of the 10,000 samples. The ensemble average goes to 0, while the single sample doesn't vanish as an impulse response. This is a very intriguing properties. Now, it means that the ensemble average shows an irreversible energy confinement property, although it does not represent any of the sample of the population. So ensemble average and samples can have a totally different nature. But now what I am asking is that I can force the sample to be the closest possible to any sample of the population. And I can do this by suitably selecting the probability density function. This is the way of reasoning. The probability density function. So what we have to do, so the mathematical point is quite sharp. So we have that this is the impulse response. So we have that omega is our omega I are random numbers. Then we can define random points, sigma, that depends on time. So time is just a parameter. Then we have that h sigma is the representation just of a summation of random variables that depends on a parameter that is time. The second definition is that we just introduce, as before, our characteristic probability density function for this point sigma in this special space. Then we have just a relationship between P sigma and PD omega. So we are interested in PD omega, but it's simpler to reason in terms of P sigma. So this is the nice relationship and simple relationship between them. So from now on, we will consider P sigma because it's easier. Then we can define the average of the impulse response, just considering this integral, and then there is the variance of the impulse response, just taking the square of the difference between the single sample and the average. So we want to minimize this integral. So the statement of the mathematical problem is this is a function of p, so find p that makes the minimum. The nice thing is that nevertheless the problem seems to be quite complicated. It is possible to find an analytical solution for this problem. So this is catching the MIVAR. MIVAR means minimum variance response. So it is a constrained minimum problem. So we have two constraints. In your presentation today, you introduced some constraints that are similar to this. So I have some constraints because we want to have the verification of this closure property, and then there is a definition of average of H that produce this result. So we can have...
and H of sigma is assumed to be null.
Yes, exactly. In fact, this remark is very good because actually the probability we are speaking about is a conditional probability. It's the probability to observe omega 1, omega 2 given H bar. It is, this is the formulation that is so-called maximum likelihood formulation for the problem. So it is the constraint that we have, and then we can introduce this modified functional. So there is the original function plus lambda is a Lagrange parameter, and then we have the constraint to satisfy. Then we can extract from this the Euler-Lagrange equation. The Euler-Lagrange equation is this one. So I just made calculation in order to provide this. Then the solution that leads to an equality for this equation is just this, and from this I can integrate in order to produce an exponential family of distributions for the best we can do for our system. I don't know why they are superimposed. So if you make some calculation and then you select among the different possibilities just the Gauss distribution, this is not exactly a Gauss distribution because you have here a function that depends on the frequency. So it is a modified frequency exponential distribution. But this is the shape that we were looking for in order to have the best solution of the problem. So this is just an example. Suppose that the environment is just a set of parallel oscillators that are all attached to the same master structure. So this is the master, so this is the mass, the spring, and then this is the environment. This is a very, very special case of environment. So it is, say, the simplest in some sense that we can consider. It is one of the systems that are considered for other reasons in literature. So you have all these small oscillators. Each of them has a different natural frequency. Suppose that we put all the masses equal each other, and then just we can randomly vary the stiffness. So what happens is that you obtain a system like the one that we are investigating. So this is the shape of the probability density function that fits our theorem. So this is the distribution that we have. As you see, it is not a normal distribution because it has an axiometric behavior. But this is the impulse response. It is very nice because it goes the best it can to 0. So it means that you can transfer the energy to the environment. You cannot do it completely, but you have some noise that remain as an interaction term between the two. We have also some physical experiments that we made in order to test this kind of phenomena. So in this case you have a T-beam. This is a T-beam. This is the main structure, so this is the master structure. It's a continuous structure. Then you can put over there a set of resonators. There are 100 resonators, are beams. And you select the frequency distributions of them, so it means the length of them, in order to fit the frequency distribution that we found. So the probability density, the best probability density function.
They are random.
They are random, actually. No, they are cut to the following the route. But if you look at the distribution of them, it follows the previous one.
And it doesn't matter where it's attached.
Oh, they are attached in this case by glue. It's
But where you put specific one doesn't matter.
no, it does matter. Yeah, of course. They must interact in a sense that they act so that each oscillator acts on the same point theoretically. So the same point in this case is just disarm. So they are put on disarm. So it is supposed that the deformation of this arm is less than the deformation of this, so that they can act simultaneously on the same structure. So it is approximately as they act at the same point. Otherwise, so we could develop the equation for this. It's very clear that the point of application is very important. So these are just the frequencies that we selected for the 100 oscillator, and these are the corresponding length. So these are the frequencies that are computed on the basis of the optimal variational problem that we solved. Then this is the comparison, experimental comparison by a laser beam between the two. So this is the response decay in the absence of the mini beams. It means that this is something that is related to what we can call the intrinsic dissipation effect of the structure.
What kind of frequency is
It is just an impulse.
in which direction?
It's in the yeah, it's orthogonal to the axis of the beam and orthogonal to the plane of the microbeams. So microbeams are, yeah, it is like this. So you have, this is the structure. Then you have the family of beams like that. So we are exciting in this direction and observing response in this direction. Okay? So a sort of antenna of. And the very nice thing is that if you select this distribution, this is the comparison of the response. What is happening, even if you look at the experiment, is the energy goes very fast to the oscillator. So fast and so strongly that when you apply the impulse to the main structure, after 1 or 2 seconds, they oscillate tremendously and they break up. So it is all the difference that you say here is just because you are introducing a transfer of energy as best you can to the set of oscillator. And this is the comparison that this is the frequency response function of before the cure. So it is blue line. So it is the impulse response of the T-beam without the microbeams. Once you introduce the microbeams, this is the impulse response of the system. So you see how it acts as an effective damper.
In this experiment, you certainly increase interaction with the air, since you put 100 these beams, so damping there is additional distance.
Yeah.
Is it important?
Yeah. Well, say that we did a calculation about the importance because we were so excited because we had numerical simulations that provide more or less the same results for a very large class of systems. So we do not attribute this to the fact of an additional real dissipation to the system. Because if you look at numerical simulations, we have several hundred of these. It's really unbelievable how fast the energy passes from the master to the satellites. It is difficult to produce the same result using traditional damping system. So damping system generally put something that is something that has the property of introducing local dissipation. So I want to, for example, I want to damp this. I put a foam over that. That means that I'm trying to transform locally the energy that goes here, in here, into heat. But here the concept is completely different. I'm exciting here. I put here an energy sink, and then I'm moving the energy far away from the point of injection of the power. Okay, so it is nice just to see. So we relied several experiments. This is the best distribution. So we just for fun modified a little bit this distribution, and these are the results. So it shows even experiment, and in that case, more or less the effect of additional damping due to the presence of the air is more or less the same. But actually that is experimentally the distribution that works.
You can do easily empty pump and let it vibrate
the one that
air, so you can
oh yeah,
be ahead of the discussion.
Mm-hmm.
Easily,
but I think that these so these are some industrial application for this.
Instead of sending in the space, it is cheaper.
But just to look at the end, because I think that it is more or less enough. So this video shows very well the effect that we have. So it is the power flow goes into the motion of the oscillators.
But these oscillators, this is random oscillators, or they're not?
No, they follow a distribution that is a little bit different with respect to the optimal. But we calculated a time window over which the energy doesn't come back as a time that is long enough for the energy to be dissipated actually into the set.
This is a beating, right?
Oh well, it is a sort of say that this theory is sort of generalization of the bit phenomenon.
Yes.
Oh, this is bits. Yeah.
But I find this is very interesting because with clever, now I will say something without, I don't want to upset you.
Oh well, I'm robust enough.
Mathematician could found a theory of irreversibility.
Well, but it is close. So I don't want to say that we don't need mathematicians. But is so I would like to say that actually some of these papers are just cited in the paper very recently in the papers in physical review letter in order to indicate that this could be a way to look at irreversibility.
And it's all linear. The surrounding ambient.
No, well, we developed it together with Nicola Roveri, some experiments, numerical experiments, and some theory in which we have a nonlinear interaction. So we investigated the effect of nonlinearity into the phenomena, and say that if you have a distribution that is different from the optimal one, nonlinearity helps very much. But if you have the optimal distribution, nonlinearity doesn't help. So this was the fundamental result, Nicola, I think, more or less. So this.
About the experiments, you will, in the videos, we always see that the master is much bigger than the small scale.
Yes, very much. If you have, this is a good question, so I forgot to mention this. It is a very big point. It's a very big point. At a certain point, I said there is a dissipation term and the reactive term. Generally, we neglect the reactive term. This is possible only if the total mass of the oscillators is small compared to the mass of the master. Otherwise, this effect cannot be achieved. So it is a good question. Yes, definitely. You are right. So it is a condition that we have to respect in order to have this very fast energy transfer.
Which again is good for statistical mechanics.
Yeah.
You have a big mass, a lot of
As a big mass.
small oscillators.
Yeah, it is a.
Heat fluxes towards the small oscillator. But it sounds little small picture there.
Yeah.
Why are you saying symmetric?
Okay, symmetric. M is antisymmetric, so M is minus.
Oh, M is not a mass balance. Okay. It's a difference.
For example, you wrote the following equation: x to dot plus x plus Hilbert transform of x is equal to 0. H is antisymmetric operator. So, for example, if you're looking for if you want to study the stability of zero solution,
if there is anti-symmetric, there is no distribution. The energy of the oscillator will cancel.
This is a case.
Yeah, right.
Exactly. So roughly speaking, his system is like this. Okay. It's just
I think I know because
you can notice this is not dissipation.
Well, it's
But it's not then it is conserved because this matrix is antisymmetric.
okay. So it's gyroscopic.
Yeah, there's
They are not gyroscopic.
but Hilbert current is gyroscopic tone.
Yeah, it is an effect.
but there is additional core. Besides anti-symmetric, there is additional one which corresponds symmetric. So there is the additional core which does.
Okay, suppose that this distribution is small, not significant, not very important. Just consider this situation. It depends on the matrix. If you consider just solutions in the form x is equal some vector exponential t lambda t, you can study the stability of zero solution of the system. It depends on the matrix M. Sometimes can stabilize solution and sometimes not. So because you wrote Hilbert operator, okay, my question is what happens to the zero solution of the system? Does it stabilize the solution or not? Hilbert operator.
Oh well, I don't know because it was not my concern about the fact that it will transform. So actually, we were looking about the viscous dynamics, so sort of.
Okay, so you have something.
But what I could say is that if you have, if you want to study stability of the system, of course, stability in the sense we use it for damping. So since the system is conservative, then you can identify a time window in which you have an increasing amplitude for the particles that you observe. In this sense, I can give you definitely a positive answer. In fact, if you observe, if you change point of view, so we are not observing the master, but you are just observing one of the degrees of freedom that you call hidden, that I call hidden variables. Okay? And then you look at one of them. In that case, these terms contribute to have a sort of instability because the trend in times is like that, of course, because they are absorbing energy. And the trend is to increase the energy. Of course, there is a limit because we know that the total energy of the system, because the system is Hamilton, is finite. But, of course, you can observe exactly in the same sense that we mentioned at the above that you can have a suitable interval over which we can observe what you say instability. It is instability in the sense that we observe for a certain time an increase in the energy. stability system. Yeah, it happens. You change point of view, you change just the particle that you're observing, and then you observe this kind of phenomenon.
So we stop.